is that we're gonna be looking at the relations. So I want us to look at the types of relations that we have. Mostly I want us to discuss the equivalence relations. So first, if we check the definition of a relation, they say that a relation R from a set A to a set B is simply any set or any subset of the Cartesian product AB. So, and they tell us that this is a collection of ordered pairs, which when we're talking about the product, the Cartesian product, they say that this is a collection of ordered pairs, X, Y, such that X is an element of A and Y is an element of B. So that's the same relations that when we are proving them, we're gonna be forced to use ordered pairs, which we'll look at those, we'll see which relations are those. And also remember that when we say that something is related, or let's say we say that X is related to Y, it can be written like this. We say that X is related to Y, or we can also say that X, Y is an element of the relation R. So this is the same thing as saying that the two of them are related, right? So we can, sometimes it will come like this, sometimes it will come like this. So we must know that this, we're talking about the subset of a Cartesian product. So now we can look at these. Let me do this. We can look at there's a certain example somewhere here which we can look at. So we can look at this. We can look at the first example. They say that let A be equals to 1, 2, 3, 4, and we must define a relation AB such that A divides B. So the question is, what do we say, or what do we mean when we say that A divides B? So if we check, we can have two statements. We can then generate two statements out of this. We can generate A over B, or we can generate B over A. So now we need to know which one is correct, right? So what they say that A divides B. So it means that the correct one should be this one. We say, right? So when we come to find the relation R, let's say they say find the relation R such that A divides B. We're gonna come and say we're given A only. We're given A, which is 1, 2, 3, 4. So we're going to replicate A and make it B. 1, 2, 3, 4. You'll see when we come to equivalence classes. Most of the times in equivalence classes, this is what we're supposed to do, right? So if we check, we're saying that A divides B, right? So it means that the numbers which we're going to take, we're going to ask ourselves, are they giving us a remainder or not? If they do not give us a remainder, then we take that number and put it as part of R, right? For an example, does 1 divide 1? Yes, we know it does, right? That's how we take 1, 1. Then we come and say, if now I have 2, 1, can this one divide 2? If yes, remember that the one on top is B, the one below is what? Is A. So when we take it, we're not going to take it as 2, 1. We are going to take it as 1, 2, according to the definition. The definition labeled it as AB. We say right now. So when we put them here, we always follow the definition. So since A comes first, we're going to say we're taking 1, 2. Then again, we come and say, if I have 2, 2, can this, let me see this. Let me try to wipe this screen. I think it's oily. I can't be able to write. Yeah. So we're saying that, let's say we have now our B is 2 and our A is 2. Is that right there? So we know that this is possible. 2 can divide 2. So we're just going to take that to be that 2. And let's say again our A is 3, or maybe let me say I do this. Again, we know that our A is 1, 2, 3, 4, and our B is 1, 2, 3, 4. So let's say I ask myself like this. Let me just highlight. Can 1 divide 1? Yes. Can 1 divide 2? Yes. You see, right? Okay, let me use this one. Can 1 divide 1? Yes. Can 1 divide 2? Yes. Can 1 divide 3? Yes. Can 1 divide 4? Yes. That's why here we have 1, 1, 1, 2, 1, 3, 1, 4. Then now you come to 2. 2 cannot divide, let me see, 2 cannot divide 1. You see right now? If I have 1 over 2, this is not possible. It's going to give us a remainder. So we're not going to work with that. 2 cannot divide 1. But 2 can divide 2. That's how we took this. Again, 2 cannot divide 3. But 2 can divide 4. That's how we have 2, 4. You see that? Now we come to 3. 3 cannot, so let me erase this. 3 cannot divide 1. 3 cannot divide 2, but 3 can divide 3. That's why now we have 3, 3. You see that? Again with 4. 4 cannot divide 1, it cannot divide 2, it cannot divide 3, but it can divide 4. That's how we have 4, 4 here. So sometimes they'll ask you these types of relations. Most of the times they ask them in quizzes. I'm sure if you have written some quizzes, maybe they have brought them, or if they haven't, means maybe they can bring it in a test. All right. So some of the relations, they come in this way. You'll see they tell you A divides B, M divides N, and so on. The relations can come in this way. Or some, they can come in such an example here. They say that let A be equals to R and B equals to R. Then they say that we define the relation on R from R to R by A related to B, if and only if A squared minus B squared is equals to 1, right? So if we check here, the relation is what? The relation is equals to AB, and they say that A squared minus B squared is equals to 1. So now, sometimes they can tell you to write down the elements which can be included within this, right? And they should be an element of a real number. So we should pay attention here. Sometimes they'll say it should be an element of a natural number. Let's say they just bring the question, they change this and say element of a natural number. Yourself, you come and write 0. You write root of 3, knowing very well that those are not natural numbers, right? So they can sometimes trick you like that. So here they say that A should be a real number, meaning the first number should be a real number, B should be a real number, the second number should also be a real number. Now, when I'm going to find these numbers, what I can do for me to find these numbers, I can make A subject the formula. You see, right? Then we know that this A will be equal to plus or minus root of B squared plus 1. So it means that I know that if A is 1, or not A is 1, if B, let's say if B is 1, let's I make B 1. If B is 1, I know that A will be equal to, this is 2. I know that if B is 1, then I know that A will be root of plus or minus root of 2. So I know that this will be like this. I can also have this possibility, or I can also have this possibility. You see that? Or I know that if B is 0, then A will be plus or minus 1. So that's why we have this possibility. So it means that we can have this possibility, and also we can have this possibility. We say right now. So now, if they tell you to label this or to write down these relations, what you need to do is first check the number that I got. Is it a real number or not? Does it satisfy this condition? If we had said that this is a natural number, it means that this would be wrong, this would be wrong. You'd only look for the ones which are natural numbers, right? So it means that here you'd only include these ones. Let's say you choose B to be 1, B to be 2, to be 3, to be 4. And then you'd write the ones which only satisfy the condition. So now, if we look at the types of relations, remember we have 4 types of relations. We have a reflexive relation, we have a symmetric relation, we have antisymmetric, and we have transitive, right? So we know that with the reflexive relation, we just need an element to be related to itself. So once an element is related to itself, we say that it is reflexive. I'm sure by the way the reflexive or the term reflexive, we must know what does it mean, right? So now, for the definition, we're saying that R is called a reflexive relation if for all, if I take A from a certain set, we say that in this case, we say the set is A because we don't want to define any set. We can just make it to be A to accommodate all sets. We say that A is an element of A such that if I take the ordered pair AA, which is an element of R, remember I said that this is the same thing as saying A is related to R. And then we say that that set or that R reflexive, and that relation R is reflexive, right? So now again for this symmetric relation, it's the same thing. We have to take the relation from R to R, and then this relation will be called a symmetric relation if whenever we take 2 pairs A, B from R, right? And we find that if I commute those pairs, I'll find that they're still in R. And that will occur for some 2 elements taken from a certain set. Always we should take those elements from a certain set. And this means that, remember, AB element of R means that A is related to B, and also B, A element of R means that B is related to A. So for the symmetric relation would be this case. But remember, when we talk about the equivalence relation, we're not going to talk about the antisymmetric. When we talk about equivalence relation, we're going to exclude this one. When we talk about the equivalence relation, we'll exclude this one when we talk about the equivalence relation, right? So now, if we talk about the antisymmetric relation is just gonna be, we're gonna say that now let's say I take 2 elements from A, and then remember from the symmetric relation we wanted to check if this is true, but in the antisymmetric we just assume that that is true, and if that is true we must check if A is equal to B. You see, right? In other words, this would be true if and only if A is equal to B. So when we do some examples, see, we just assume that these 2 are true, and then we show that A is equal to B. If that is the case, and then we say that that relation is antisymmetric. Right. Then when we check the last definition, it says that the relation R from A to A is called a transitive relation if for any A, B, C. So for this one, we need, this is the only one that we need 3 elements, which is a transitive relation. If we take 3 elements from a certain set and we see that like this, then we say that A is related to B. Let's say A is related to B, and again B is related to C. This simply means that since you see they share a common element BB, so this will simply mean that A must be related to C. So that is what we're going to be proving. So here we're just going to assume that this is true, then we show that also this is true. You see, right now, if we check in this definition, they say that this will be true. If this is true, then this is also true. So that is what we must show. We assume the hypothesis. We have learned about the hypothesis in logic mathematics. We assume the hypothesis and show that the conclusion is true. You see, right now. So that will be our aim for this transitive relation. So now we can look at an example. The example they say, let me just copy this example, and then we can write it. They say that the relation R, now check, our set is what? Is Z, right? From Z to Z defined by x related to x if and only if x is equals to x. Alright, so I'm going to copy this, then we create a new page so that we can solve it fast, right? Now let's say we're given this question. They say that the relation R from Z to Z defined by x related to x if and only if x is equals to x, right? Let me see, is it x equals to x? Let me see, it's supposed to be x equals to y. Let me see the question. Oh yeah, x equals to y. Yeah, let me do this. Yeah, like this. So first thing that we're gonna do here, we're going to say on the solution, yeah, so we're gonna first check reflexive, right? For reflexive, first thing that we do, we should know that for reflexive we need one element. So we're going, first thing that how I want you to solve it, I want you to first take an element. Let's say let x be an element of z. We know that this is defined from z to z. Let x be an element of z. Then I check this. They say that, let me do this. They say that for this to be reflexive, x must be related to itself. You see, right? If I have x element of z, and I check if I take this, if I take x related to x, this would simply mean that x, I don't know why this screen is doing this. Yeah, this would simply mean that x is equal to x. We say right now, if x is related to itself, this would simply mean that x is equal to x. But even though the definition says this, I want us to start by checking the equation for the equal sign. Are they equal? You see right now. So I want us, since this is saying if and only if, it means that we can start anywhere. So we can start by saying x will be equal to x, which this simply means that x is related to itself. You see right now that we can say hence R is reflexive. We say right now, let me, I'm coming back. Yeah, so since we see that R is reflexive, it means that we can now say that we can check the symmetric, right? So now we can check symmetric. Yeah, let me hope this, yeah, this pen now, I think it's fine. now we can check symmetric, right? So when we come to symmetric, now for symmetric we need two elements. So we need to let, this one is one of the simplest, right? We need to let xy be an element of z. And then after that, the definition say that, so here we're going to take the definition as it is. Is that it say that x is related to y, not this type of y, yeah, it's related to y if and only if x is equal to y. So for us to prove that this is true, now we must arrive where we say that y is related to x. So for us to arrive there, we must apply commutativity. So that somehow I must commute, take this one to the other side, this one to the other side. Then we have this, you see right now. So from here, I'm going to divide both sides by negative. Then I'm going to get y is equal to x. And this will only occur if and only if y is related to x. So now we see that this is true. So we can say hence R is symmetric. We'll say right now. Then now after checking this one of symmetric, we can now check transitive or antisymmetric. Let me see if we can check antisymmetric. Let's check symmetric. So with antisymmetric, you also need two elements. You're going to let x, y be an element of z. And here, remember they say that we must assume that these two are correct. So it means that I must assume that x is related to y if and only if x is equal to y, and I must assume that y is related to x if and only if y is equal to x. So if this is true, this simply means that x is equal to y. So that was the case. We wanted to check if x is equal to y. And when we check this, we see that it's true. Right? We see that it's true that x is equal to y. So that is how symmetric is. If we can check here how they solve the antisymmetric, let's see the antisymmetric. They say that since these two are true right now, are related to itself, then x is equal to y. So that is what we needed to check there. And if we check the symmetric, they say that if xy is related to y, this means that x is equal to y. Hence, since equality has commutative property, that is what I applied there, then we can arrive where we say that y is equal to x, which means that y is related to x. So R is symmetric. So as we are going to arrive there by showing by calculations, you see right, where I showed all the steps to how did I arrive there. So what I did here, I applied commutative property. You see right now what I did there, just applied commutative property. And then now we can check the transitive. When we check transitive, remember for transitive we need three elements. We need x, y, z, element of z. And we say that we must assume that this and this are related. Is that right? So it means that I must say that x is related to y if and only if x is equal to y, and again y is related to z, and again y is related to z if and only if y is equal to z. Then for us to prove that since the two have a common element, it means that they are related, right? X and is related to z. So for me to prove that, I'm gonna say then, so let me just imply, or just imply from there. Since we see that they have a common element, I'm going to imply that if now I take this and add it with this, or subtract, can do any, but I can add. I take x, so I'm gonna first add the left hand element and then add the right hand element. If I take x plus y, which is equals to y plus z, this implies that if I take y to the other side, they will cancel. This implies that x is equals to z. And what does it mean when x is equals to z? This can only occur if and only if x is related to z. You say right now, when x is equals to z, according to the definition, says that this only happens if the two are related. So now we have proven this according to transitivity. Then we can say that, hence R is transitive. And we know that if R is reflexive, symmetric, and transitive, we know that this is called an equivalence relation. We call this an equivalence relation. We say right now, if R is reflexive, symmetric, and transitive, we call this an equivalence relation. So for sure, you might know how to define an equivalence relation, because that one usually they bring the definition. So we know that we can say that R is called an equivalence relation if it is reflexive, symmetric, and transitive, right? That is how simple it is to define such a definition. So now we have this one where they say that x is greater or equals to y. So I can now explain this. We say that the relation R from R to R. Now this is defined in real numbers. They say this is defined by x related to y if and only if x is greater or equals to y. Sometimes instead of saying if and only if, to just put this sign to show that this is if and only if, right? So I'm gonna use that. So now when we check, we're going to say, now let's prove that. We're going to prove that. Now let's just paste it here. Now we're saying that the relation R from R to R is called, let's say we start by proving reflexive. Let's see if this thing will be reflexive, right? So let me tell you something, right? Whenever you are proving reflexive, this reflexive is always true as long as there's an equal sign. You say right, if there's an equal sign, it means that it's always true. You say right now, reflexive will always be true if there's an equal sign. So first what we're going to do here, we're going to let one element, which is x, be an element of R, which is a real number, this one, right? Then we say that here, x will be greater or equal to x if and only if x is related to itself. And this is true. There's an equal sign there. You say right now. So I'll say hence R is reflexive. You say right. Then for symmetric, I need two elements. And then I take the definition as it is. The definition says x is related to y if and only if x is greater or equals to y. Remember, after taking the definition, we need to commute. So I'm going to commute this. And then I divide both sides by negative. The sign will change to this. So check this. We were supposed to get the aim for us to get, let me commute it. Let's say I change this to this according to that definition. What we're supposed to get is this. we're supposed to get that y is greater or equal to x, but we didn't get that here. We got the original statement, right? So this simply means that R is not symmetric. You see right now? So we can deduce that. We say hence R is not symmetric. You see right? Because we couldn't get y greater or equal to x. We're supposed to get that, but the sign changed according to this negative. Remember, inequality signs change. So sometimes, even though there's an equal sign, the moment we say inequality this or inequality sign, sometimes it might not be true. You see right? That this might be symmetric. Sometimes it's not true. So now we can check, let's check antisymmetric. So even though this relation is not symmetric, when we come to antisymmetric, we're going to let x, y be an element of a real number. Then we say that if here we have x related to y, which this means that we know that this means that x is greater or equal to y, and we have that y is related to x. Here we must just assume, even though it was not symmetric, we must just assume that this is related. It's true. You say right now, we must just assume that this is true, even though in the symmetric it was not. You say right. Then we say this will imply, if that is true, this will imply that x is equal to y, because there's an equal sign. So this will be true. You say right. Hence, R is antisymmetric. Yeah, then we see that. Then now we check transitive. For transitive, we're still gonna need 3 elements. We let x, y, z be an element of R. Then we know here that we're supposed to say that if x is related to y and y is related to z, we say that if x is related to y, this means that x is greater or equal to y, and y is related to z. This simply means that y is greater or equal to z. So this now we're going to check if x is related to z, because they both have a common relation, which is a common element, which is y. So we're going to add them, right, as we do. X plus y, I first add the 2 ones here, then I add y plus z. Then we see, we want to check if x will be greater or equal to z. And then this will imply that if I subtract y both sides, I'm going to have that z is greater or equal to, your xz is greater or equal to z. And this will occur if and only if x is related to z. You see right now? Hence, R is transitive. We say right, hence R is transitive. So if we want to check for an equivalence relation, we see that this is symmetric, it's a reflexive, but it is not symmetric, and it is transitive. So it means that this won't be an equivalence relation. You say right now, not an equivalence relation. So this won't be an equivalence relation. So it means that when we are going to prove questions that ask us to check if this is an equivalence relation or not, it will be simple for us to check. All right. So now let's see if we have. Yeah, I think these are the first 2 examples here. Now, here we come to an equivalence relation, right? They say that a relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. So here we exclude the idea of antisymmetric. So we no longer check antisymmetric. You see right now. So we only focus on reflexive, symmetric, and transitive. Now, let's say this. Yeah, for now we can skip this example. We'll do it when we meet. So we can look at this. They say that let R be a relation from R to R defined by x related to y if and only if x minus y is divisible by 10. And here likely they tell us what does it mean. Sometimes they don't, right? But you must know if they say that x minus y is divisible by 10, it means that it must be a multiple of 10, or it's equals to 10k for some k element of integers, right? So now for us to show that this is an equivalence relation, we must first show reflexive, we show symmetric, then we show transitive. All right, so now what we're going to do first, we see when we check the reflexive. Now remember, for the reflexive I always want you to say let x be an element of, this one now is defined under R. You say that, you say let x be an element of R, and then you use the formula. The formula says that x minus y, so it means that I can say x minus x because x is related to itself, right? And this will give us what? 0. And 0 is still the same thing as, they said it must be a multiple of 10 or divisible by 10. So it means that it is indeed a multiple of 10 or divisible by 10. 0 can be divided by 10. So now we say that it's true, right? Hence we can say, hence like they said, this is divisible by 10. So we say that, so R is reflexive. Then when you come to antisymmetric, when you come to symmetric, still we're going to let xy be an element of R because it's defined on R. After that, then we suppose that x is related to y, or we don't even have to suppose, we just take x related to y. And then we know that this is true if and only if x minus y is equals to 10k for k element of an integer. You write that also. Then we show that if I commute these two, I'm gonna commute them like this because they're on the same side, right? So when they're on the same side, you commute them like this, you don't take them to the other side. Then after commuting them like that, now I factor out y. Your negative, I factor out the negative to find this. You see, right? And then when I divide both sides by negative, the negative will be taken by k. This will be y minus x, which is equal to 10 minus k. You see, right? So here they just skipped this step of commuting. So we see what it is. So we're gonna get this. And we know that this minus k is an element of integer. Right? So it means that this is divisible by 10. X minus y is also divisible by 10. So it means that this implies that y is related to x. So if that is the case, it means that R is symmetric, right? Then for transitivity, we're gonna need 3 elements. We're gonna let x, y, z be an element of a real number. Then we take these two to be related to each other, right? I'm gonna take x related to y if and only if x minus y is equals to 10k and y related to z if and only if y minus z is equals to 10. I'm no longer gonna take k because I've already used k here right now. I can just say 10p. Then I say for kp element of an integer. Now since I have these two, I can now say then, because now I want to show that x is related to z. So since we know that we always add them, we're just going to add them even here. We're going to have x minus y plus y minus z, which is equal to, then I add 10k plus 10p. Then this will be, y will cancel each other. We're going to have x minus z, which this will be equal to, this will just be equal to 10k plus p. Indeed, this is a multiple of 10. And then we show that k plus p is an element of z. You see right now? So we can do that. Let me see. Yeah, here they just, instead of P, they chose H, which you can still do that. For some KH element of Z, then we ourselves, we know we add them. Then we will find that this is equal to 10K plus 10H. Then you factor out that. You find that indeed K plus H is an element of an integer, which means that this is divisible by 10. If it is the case, then it means that R is transitive. You must state that. And since R is reflexive, symmetric, transitive, even though they didn't conclude here, you must state that thus R is an equivalence relation. You said right, you must state that R is an equivalence relation. So if that is the case, then we can stop here. If you have any question, you can ask. If not, it means that we have to stop here. So it means that next time when you come back, next time when we meet, so again we're gonna be meeting contact. It means that we'll do the equivalence classes and partitions, and then we do the mod congruent modulo, and then I think in the next class we can just do those two. Yeah. Then after that we do the tutorial. Then we go to functions. Any question? If not, it means that I can stop.